Okay, welcome back everybody. We are on section 4.4, and this is probably one of the most referenced sections in the book. So like for the rest of the semester, we're really going to be paying a lot of attention to this theorem 4.4.1, and that's that it converts nth order ODEs to first order ODEs. And I wasn't quite clear about this in the last section, though I should have been. It was included in the definition of an ODE, but I didn't really describe it very well. The top number of derivatives of an ODE, so in this case n, that's the order of the ODEs. So the top number of derivatives is the order. So that's just something to keep in mind. This is an nth order ODE. And there's this very nice idea that if we can convert an nth order ODE into a first order ODE, then we really only need to study first order ODEs because, well, everything's a first order ODE then. So there's a theorem that actually lets us do that. And this is the theorem 4.4.1 that, like I said, we're going to reference all the time. So we're going to start with kind of the general ODE in nth order here, but we're going to end up with a modified ODE here for a new function g. There's a function f. We have a new function g, and we have new variables y and y prime, but all of a sudden all of these x's, zero derivatives up through n derivatives on x, all get shoved into just a single derivative. And that's really the special thing about this theorem, is that we can reduce everything to first order. So the way we do this is it's important that we recognize we have an nth order ODE, and that we're assuming that our solution exists in d dimensions. Okay, so we have to keep this in mind. Nth order d dimensions, then we get a first order ODE in n times d dimensions. So we have to multiply the dimension of the order, well, the number of the order, with the dimension that we're evolving in, and then that's where we end up with the new ODE is evolving in a lot more dimensions, but we can save ourselves on the order. So I'll add that in here. So maybe I'll say the price we pay for reducing order is increasing dimension. And in fact, those two numbers, the order times the dimension, will always multiply to be the same thing. So we always have n times d, where n is the order and d is the dimension, will be the new dimension of the modified ODE. So let's actually see how we do this. I'm going to go through the proof, but I'm only going to highlight like specific parts of the proof. I'm not going to completely go through the entire proof because that's not important necessarily for how we would do this practically. So the way we're going to think about this is like we have our original ODE, and what I'm going to do is I'm going to define my vector y, and the vector y is just going to get defined. Each entry in the vector y is going to be defined by the n-1th derivative on x. So y1 will be x0, y2 will be x1, yn-1 will be xn-2, yn will be xn-1. Now, we have to keep in mind, though, that if this is in d dimensions, then this is in d dimensions. Okay. So really, it looks like this is a vector of length n, but if each entry in the vector of length n is actually d like variables long or d dimensions long, the entire vector actually has length nd. And so that's where our nd is going to arise from. And so if we just make this as a definition, we're going to define this special function y as the vector of all of these. And then we're going to recover some really nice properties about y. So the first thing I want to recognize is that every single one of these entries in my capital F, that's just y sub n, well, that's y sub n prime, that's y sub n, then we'd have yn-1, and all the way down to y2 and y1. So we have yn prime right there, and then we have the rest of the entries of y, and they're going to all be encapsulated into just y by itself. So it turns out that this capital F is looking at the derivative only at the very last term, and then the rest of the terms, all of them together. And so there you can already see we've done like half of our job. We've already reduced this function f from an nth order ODE now to a first order ODE, where the order of this variable is first order, and it's only the very last component of y, and then we care about the rest of the entries in y. And then, in fact, we have to recover a we must recover an ODE relationship for each of these. So each of the y's that are sitting in the y vector need their own ODE relationship, right? Because y prime is actually y1 prime, y2 prime, dot, 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 yn prime. And right here we have a relationship of yn prime that's going to be equal to 0 because the capital F of the inputs is equal to 0 in my original ODE. So I have a relationship for specifically this term of y prime, but the rest of the terms in y prime, I will have to derive a relationship for those. So if I scroll down a little bit, I notice that y1 prime happens to be y2 just based off its definitions. If I take a derivative of y1, which I've defined to be x0, if I take a derivative of that, I have to get x1. Well, x1 was y2. So really, I've jumped from y1 over to x, take a derivative, and jump back to y2. So I know that y1 derivative is y2. I know that yk derivative is yk plus 1. And so this is how I establish, this establishes the rest of y prime. Right? Y prime needs to consider a prime on every single term, and these definitions establish those for me. So what I get from that is the following. If I want to say, let's say I convert this equation here, I convert it as an equation. What equation is that? That's y1 prime minus y2 equals 0. Or down here, it's yk prime minus yk plus 1 equals 0. Okay, so the left-hand side here is where I'm going to gain the entries of what I call G. So those are all the relationships that y prime has, each y prime up to n minus 1. And then finally, we discovered that the nth y prime, yn prime, has the relationship that f should be equal to 0. So this is how we're going to define G. My new function in nd dimensions will just be y1 prime minus y2, y2 prime minus y3, all the way down until I get up to yn, and then once I reach yn, that prime is the one that ends up inside of my original function. So this is now the vector valued function g with vector inputs, and the equation g equals 0, I would notice if I set this ODE, or if I set that function equal to the 0 vector, then what I recover is exactly the relationship to recover every single vector from its previous components, and then the very bottom one was the original ODE. But now everything is truly sitting as a first order ODE, so that's really nice. Okay, so that's just what we want to think of when we have these, and let's look at an example, right? Because that's kind of, without an example, the theorem's not going to mean much to us. So we look at this nice example of a third order ODE, and it's going to be in one dimension, okay? So a third order ODE in one dimension. We're going to move to a first order ODE in 3 dimensions. So this third order ODE looks like x with 3 derivatives plus 2x with 2 derivatives minus 3x with 1 derivative plus x equals t. And if I follow the process of, what I want to do is first recover this capital F such that it's equal to 0. I'm just going to move everything to the left-hand side. So the t is going to come to the left-hand side, and that helps me define capital F. I've moved t to the left-hand side, and that's equal to 0. And I notice that this is a function of t, x with 3 derivatives, x with 2 derivatives, x with 1 derivative, and x with 0 derivatives. Now all I have to do is follow the procedure as outlined in the theorem and define my y, vector y, right? My y vector as the first entry is x, the second entry is x prime, and the third entry is x double prime. So I've defined a y vector to be the 0th first and second derivative of x, but I'm renaming them y1, y2, y3. Following that procedure, then, I can just define g directly as it was in the procedure. We'll recall that the first entry of y was y prime, y1 prime minus y2. Second entry of g was y2 prime minus y3. And you would continue until you reach your top value of y on the right-hand side there. Okay, so there's y3. And then the final entry is this capital F. Okay, so if we translate capital F and we put the right entries for y in each of their components, that's y3 prime, y3, y2, y1. So there's y3 prime, y3, y2, y1, and then t sits along for the ride. So all of a sudden, there's my g that I care about. This is g of now only one derivative, but in 3 dimensions. One derivative is on each term, but it exists in 3 dimensions. And if this vector is equal to the 0 vector, I have the original ODE I care about. And in fact, if I want to modify the ODE into some sort of explicit form, I can rearrange this equality, each row of my vectors, right? Now this is just a system of equations, into what looks like a first order system of equations. And in particular, these are functional equations. And in particular, these are functional differential equations, right? So I can rearrange, that's the system, that's the first order system of ODEs, which would describe, if I decided to solve this system, it would describe the original third order system of ODEs, but it's really not a system, it's just one ODE. So I can convert a third order ODE in one dimension into a system of 3 ODEs, but they're all first order, right? So I have 3 dimensions first order. How would we actually recover the solution x, right? The solution x that I cared about at the end of the day, this one, that solves that ODE. How am I going to recover that from my system? Well, I just recall this definition that y1 and x happen to be the same. So since y1 equals x, by finding y1 in the system, I've found x, which is my actual solution to the ODE. Okay, so and that's what I state at the bottom there, right? If I solve this system of 3 first order ODEs, they all depend on each other. If I solve that system, I just look at my solution y1, and that's going to be x, which solves the original ODE. This is just like, maybe I'll mention that here. This is just like how you would solve systems of linear equations with matrices, right? You would finish that and then you would notice, okay, the solution to the first one is actually the first entry in my vector is the solution, one of the definitions of the solution of my system. All right, I've provided a second example here. I'm going to jump through this example a little bit faster since we've already seen it once. We are now changing the dimension and the order. Now we're working on a second order because I have 2 derivatives there and 2 derivatives there. And I'm actually already started in 2 dimensions, right? So I have an x1 and an x2, or you can think about this as a system of 2 ODEs. So I'm in 2 dimensions, second order ODE in 2 dimensions. That means if I want to jump to a first order, I take 2 times 2, and I'm going to end up as a first order ODE in 4 dimensions. So let's see how we do that really quick. We're going to first define bold x, or the vector x, as these entries x1 and x2. I want to consider them collected as one vector. So I define that. And then their first derivative is just x1, x2 prime, and their second derivative is x1, x2 double prime. And then I can follow my theorem. And in following my theorem, I notice that I can find f, the capital F, which needs to be equal to 0 at the end of the day, by moving once again everything in my system to the left-hand side. So I bring the minus 3 plus x1 double prime to the left-hand side. I bring sine t minus x2 to the left-hand side. You'll notice that's where they are on the left-hand side now. And then those are equal to the 0 vector. So that's my capital F. And then also in the procedure from the theorem, I define my y to be the vector y1 and the vector y2, which are defined as the vector x and the vector x prime, which I've written explicitly there for you. So you can see I'm basically placing the vector x1, x2 on top of the vector x1, x2 prime. And I'm going to define those as, in this case, I'll call them y11, y12, y21, and y22. I could have called that y1 through y4 if I wanted to, but I want to harken back to that this first index 2 refers to this y2, and the first index 1 refers to that y1. Meanwhile, the second index 1 and 2 refer to x1 and x2 in both of them. So there I've defined y, and we follow the procedure a little bit, and we see that our g is always defined as the vector y prime 1 minus vector y2, and then we would jump down to vector y2 minus or prime minus vector y3 and so on until we got to the top y, and I'm noticing a typo here. This is definitely y2. Until we get to the top vector y, and in this case the top vector y is just 2. So then on our second row we plug f in. But recall that this is a vector, that's a vector, and f is a vector. So each one actually takes up 2 entries inside of the true vector. And so I just put my first entry in y1 prime minus y2 up there, second entry in y1 prime minus y2 there, first entry in f there, second entry in f there. And that constructs g for me, and that g is precisely the one that when set equal to 0 is equivalent to my ODE. I can rewrite that then as explicitly as the vectors equal to each other. The g vector here equals the 0 vector, and if I decide to isolate the prime terms, right, y11 prime, y12 prime, y21 prime, and y22 prime, I can isolate all of those on the left hand side and get myself actually a system of ODEs. So this is a system of 4 ODEs, all in first order, and they all evolve in one dimension, but there's a system of 4 of them, so really I have my 4 dimensions sitting around. Okay, so we want to get really used to this. Once again, I would find x1, it would just be y11, and x2 is y22. We really want to get used to this because this is how we're going to derive all of the future formulas for higher order ODEs. So I'll mention that here. We will use this idea immensely as if we solve a first order ODE in arbitrary dimension, we can solve any order ODE in any dimension as well. So that's really the important thing. We're going to extract some formulas for some higher orders of ODEs using this technique. Let's just talk briefly about solutions. What would it mean to actually solve a differential equation? And this is the same as kind of what we were doing in the last class, where we just need to make a definition of our unknown variable, which in this case is a function, right? These are functional equations. So our unknown variable x is a function of t. So if we make a definition of this x as a function of t, so that when we take the necessary derivatives of it and plug them in, all of our equations become true. Right, every equation should be true. So let's look at some examples of these. So if I look at the ODE, y prime is 4 over ty plus t squared. I'm going to make a definition. I'm going to define a possible candidate y, and this y that I define as a possible candidate will be c1, any constant, okay, I'm just going to call that a constant, t to the 4th power minus t cubed, okay? So if I just start with that, I say I'm going to define y to be like this. Now I need to verify the equation is true. I evaluate its derivative, and I get 4c1t cubed minus 3t squared, and I plug both into the equation, right? So what I'm doing here is I'm taking the y prime there, and I'm plugging y prime in for y prime. I'm taking the y here, and I'm plugging y in for y. Okay, so if I plug that specific definition of y into my differential equation, I'm going to plug it in, and I'm going to simplify. And upon simplifying, the left-hand side, I'm leaving the same as 4c1t cubed minus 3t squared is the left-hand side. The right-hand side simplifies to 4c1t cubed minus 3t squared, and so long as both sides are equal, right, both sides are equal, that makes an equation true. Right? Once both sides of the equation are equal under some definitions, that's what it means to be true. Okay. So with this said, we have these special cases of problems of differential equations, and we call these initial value and boundary value problems. And I'm going to tell you why these are particularly useful problems. So if we look at this remark where a standard functional equation tf equals 0 is solved by the preimage of the constant function 0 under t, then we already know, just based off of equations in general, we could either possibly have 0 solutions, right? The equation could just be ill-formed in the sense that no solutions exist. We could have one solution, or we could have many solutions. And in particular, if we try to predict the future, I was calling on this before, if we try to predict the future, we would like exactly one solution. So this is like a very special case of functional equations, or really equations in general. It's the special case when we have a unique solution. And that's the point of initial values or boundary values, is they allow us to gain uniqueness out of solutions. Okay, so let's look at one of these functional equations, right? It's not a differential equation, just a functional equation. And we already encountered this one in the last class. I had said that this functional equation could be solved with an f defined with 1 plus 2 root 2 and 1 minus 2 root 2, really on any sets I define. As long as those sets are well defined in the real numbers, then that function would satisfy the equation, so there's no unique solution. But if we decided to impose a condition, or if we add a condition onto f, we say, you know what, I'm going to let f be strictly non-negative, right? It's going to be greater than or equal to 0. Then all of a sudden, I reduce the space of solutions that are possible, and I recover that, right, if this is how I would say, maybe I add the condition. So there's my original equation, and now I've added a condition to it. Now all of a sudden, I only get one solution. This is the unique solution, because any other choice where I use the negative solution to the numerical equation in f is going to give me a function which is at least negative in one place. And so all of a sudden, by adding a condition, I gain uniqueness. That's what we want to think here. So adding conditions gives uniqueness. Here's a nice proposition. An ordinary differential equation of order n. So if I take nth order, I need at least n evaluation conditions to guarantee uniqueness. At least n, right? In some cases, even that doesn't give us uniqueness, but I will require n evaluation conditions. So for example, given our standard ODE, nth order, I need at least n defined values of my solution, right? X is the solution. I need to define at least n of them. This is a set with n values in it. I need to define n of these to be some specific number xj. And once I do that, I gain uniqueness. So written another way, I would probably write this as a system. This is written as a big system where only the first entry is the ODE, and the rest are evaluation conditions which guarantee uniqueness. So that's the way we're going to see a lot of our ODEs show up, is actually as systems where the first entry is an ODE and the rest are all evaluation conditions which are guaranteeing uniqueness for us. Okay, so the first case of these is what's called the initial value problem. And what's special is that here we can see the system where the first line is the ODE and the rest are evaluation conditions. For an initial value problem, all evaluations take place at the same place, and I should say in time. Okay, the idea is that this thing is actually happening in time. So the same point in time is all evaluation conditions. So you can see every evaluation condition here happens at t naught, t0. That t0 is called the initial time, and each of these values, x1 through xn, which have been prescribed for us, are called the initial values. And so an initial value problem just says all evaluations take place at the same place in time, or the same time. Okay, the reason why these are natural in physics, for example, is that if we take a snapshot of the present, right? Take a snapshot of the present, we often know the present velocity, acceleration, etc. of an object. If I'm driving in my car and I wonder where it's going to be in 10 seconds, I know the current speed and I know the current acceleration if I measure enough things right at that moment in time. I should also know the current acceleration and so on. We do have a second type of condition, though, that's pretty common. There's actually more conditions than this, but this is another one that's common. That's called the boundary value problem. And you've noticed I've switched my variable here, my dependent variable, or my function I'm solving for, from an x to a y. And that's just because a lot of times we talk about x as a position, which depends on t time. So the position of a particle dependent on time is associated to initial value problems. The quantity y, as it depends on space x, is often used for boundary value problems. So that's why sometimes you'll see y as the dependent variable with x as the independent variable, but sometimes you'll see x as the independent variable and t, or x as the dependent variable and t as the independent variable. Okay, so a boundary value problem is just very slightly different than an initial value problem, with that difference being right here. Notice that all evaluations take place at 2 points in space. Okay, so we have a lot of evaluation conditions in either case. The question is, do they take place at 1 point in time or 2 points in space? And of course, by time and space, I just mean the independent variable. So am I evaluating at 2 different places or only at 1 place? And that's the only difference between the two. Boundary means I'm evaluating on the boundary. And in PDEs, it turns out to be a little bit more difficult than that. But at least in one dimension for ODEs, that means I'm only evaluating at 2 points in space for boundary value problems and 1 point in space for initial value problems. Okay, and this is what I was talking about earlier. We've switched notation from Tx to xy. T is temporal input, x is spatial input, and then x would be regarded as a spatial vector, which evolves over time. Y is regarded as a quantity, which changes over space. And these are two very physical ideas that you can give ordinary differential equations. Okay, so let's look at some examples. Here's a first order ODE, and it has one condition. And the nice thing about first order ODEs with only one condition means that they're always evaluated at exactly the same place. So this is automatically an initial value problem because all evaluations take place at the same time. There's only one, so it takes place at the same time. All right, and then if we look at this one, both evaluation conditions, y at 0 is 1 and y prime at 0 is 0, both take place at t equals 0. And so we still have an initial value problem. If I look at the following, though, I evaluate y at 1 or at 0 in one case, and I evaluate y at 1 in another case. So I'm evaluating at 2 different points. And so we actually have a boundary value problem. And in particular, we can consider this evolving or differing over an interval, with boundaries of the interval being the 2 points I evaluate at. So in some sense, I'm thinking about the function only existing on that the interval. Okay, and then this final chapter, or the final section, just stick with me really quick. I provided what I call a map of the difficulty of differential equations. And this is because this is the end of the introduction part of our book. We're going to start diving into real differential equations in the next section. And I just want to say, hey, this is what differential equations kind of looks like with respect to the real world. We start with finite dimensional linear ODEs, and then we can either build our way to infinite dimensional linear ODEs, or we can build our way to finite dimensional nonlinear ODEs. But possibly from infinite dimensional linear ODEs, we could also head over to finite dimensional linear PDEs. And this being PDEs, everything in purple is a PDE, everything in orange, salmonish is an ODE. And these are kind of how they all relate to each other, with the most difficult being down here and the least difficult up here. Okay. And so thinking about it like that, in this course, we're going to do our best to cover these a little bit. And because over here, these are actually a little harder than these, that's why linear PDEs can kind of be an easy stepping stone after you take this course. That's why this course is kind of used as the introduction. But primarily, we're going to be covering what's in the upper left corner here. All right, that's all I have. Thank you very much for sticking with me. See you in class.